Okay, so this is lecture number 2. And again, today we are going to learn about model number 1 and review of MOSFET operation and fabrication. So I have shown here various MOSFETs basically. One MOSFET is bigger and then it's smaller than earlier one and its size is reducing. Actually, the purpose to show all these MOSFETs and in reducing order of area, because we are going to learn a topic which is called as MOSFET scale. Okay, so MOSFET scaling. So what we are going to learn in this particular topic. So objectives of the lecture number 2 are to understand concept of MOSFET scaling. So you will know that what is meant by MOSFET scaling. Then to know what are the different types of MOSFET scaling. Then to analyze impact of scaling on MOSFET performance, and then to discuss advantages and disadvantages of MOSFET scaling. Okay, so these are the things which we are going to learn in this particular topic. Okay. Then what are the outcomes? Outcome is after successful completion of this lecture, what you will gain. So first, you will be able to know, you will able to understand concept of MOSFET scaling. Then you will know what are the different types of MOSFET scaling. Then you will analyze impact of scaling on MOSFET performance, and you will be able to discuss advantages and disadvantages of MOSFET scaling. Okay, so let us first begin with the history of MOSFET scaling. So if you remember, this was whatever I'm showing, this was first computer. And this computer was called as ENIAC, first electronic computer, which was built in between 1946 to 1956. And we call this as first generation MOSFET. First generation computer. And this computer was made with the help of vacuum tubes. So whatever you see here, these are basically vacuum tubes. Whatever you see here, these are the vacuum tubes. And if you want to know the specifications of this computer, weight was 27 kilograms, 27,000 kilograms.
Yes, sir.
18,000 tubes were there, 18,000 devices. You can say that 18,000 tubes were there or devices were there. It was consuming power of 150 kilowatt. You can imagine how much power, 150 kilowatt. Then its area was 1800 square feet. 1800 square feet is, it's very huge area, very large area. You can say that our classroom is all 56 square meter. And if you convert that into square meter, square foot, you need to multiply by 10. That is 660. So you can say that 3 classrooms means that was the space occupied by first generation computer. And speed was only 100 kilohertz. Speed was very low. And its reliability was poor. Reliability means ability to work continuously without failure. So, 2 minutes, one component was failure. So therefore, its reliability was also very poor. But this was first generation. Because at that time only vacuum tubes were available. So therefore, scientists have created this computer with the help of vacuum. Now, if you see where we are today, we are having laptop, we are having cell phones, smart cell phones. Okay, And you know that power of this laptop is very, very high as compared to first generation computer. Even this cell phone is doing everything right. Then why? Means first computer was occupying 1800 square feet, and this you can hold in your hand or in palm, and its computational power is many times greater than first generation computer. And this both application uses VLSI chip having millions of transistors. Okay,
Yes.
so this is current state of our VLSI. And why this has happened? This has happened because of MOSFET scaling. So we will understand what is MOSFET scaling. So let us understand some history. Because first computer was built up with the help of vacuum tubes. But you see these three scientists, John Bardeen, Walter Brattain, and William Shockley, what they did, they invented first transistor. Okay. And they received a Nobel Prize for that in 1956. This is one of the reasons why we are having very compact electronic gadgets. Second thing is Jack Kilby. This Jack Kilby has given the concept of integrated circuit. So earlier was discrete electronics. Integrated electronics means integrating all components of the circuit on same chip or same substrate. So
Okay.
1956, he had just given the concept, and in 2000, he received Nobel Prize for his concept. So Jack Kilby also responsible for this miniaturization of all electronic gadgets. The next is main person, which we call as Moore or Moore's law. So what is meant by Moore's law? In 1965, so Moore was founder of Intel Corporation.
Okay.
So Intel, you know that a very leading processor
Yes, sir.
manufacturer, they are
Yeah, yeah.
fabricating numerous integrated circuit. In 1965, he saw that number of transistors on given chip was 100 to 200 in 1965, and he predicted that after every 2 years, number of transistors will double on given chip. Yes, what was his prediction? That number of transistors will increase after every 2 years. And that become true basically. That
Okay.
was just prediction, and that has become true. And in 2020, you can say that there are more than
Yes,
billions
sir.
of transistors. There are billions of transistors, more than billions of transistors. Given processor. Right now, we are calling as quad core processors. So they are having billions of transistors.
Yes.
And why this has become possible? Again, this is Moore's law. It started with only 10 or 100 transistors, and right now number of transistors per die are 10 to the power 10 or billions of transistors per year. Okay, and most of the chips are memory chips and microprocessor chips. So whatever is this red curve, that is basically memory chip. 2G transistors, 2 giga transistors are there, and these are microprocessors. Then how this has happened is in 1956, our computer was occupying 1800 square feet, and now we can put a very powerful computer in our palm or in our hand with, and its computational power is also very high. How this has happened? Because in each and every VLSI chip, fundamental component used is this MOSFET. Yesterday we all learned about this. It's having
Yes,
four
sir.
terminals. This is substrate, this is gate, this is drain, and this is source. Two-dimensional are very important for MOSFETs. This is lateral dimension. This is called as width of the MOSFET from this point to this point, width of the MOSFET. And junction and uh, distance between source junction and drain junction is called as length, or it is also called as channel length, right? The region between source and drain under the gate is called a channel region. Okay. So channel length, as I have mentioned here, channel length and width of the MOSFET are continuously decreased. What is MOSFET scaling? MOSFET scaling means width of the MOSFET and length of the MOSFET is continuously decreased. And this process is known as scaling of MOSFET, and therefore devices are becoming smaller and smaller. Means after every 2 years, this width and length are scaled. For example, if today my length is 1 micrometer and width is 1 micrometer, and if it has scale to 0.7 micrometer and 0.1 micrometer, then earlier my area was 1 micrometer multiplied by 1 micrometer. It was 1 micrometer, right?
Yes, sir.
I may write here. Okay. Okay, so earlier my area was how much? 1 micrometer multiplied by 1 micrometer square, right? So that was 1 micrometer square. Now what I am doing, I am scaling my length to 0.7 micrometer, width also to 0.7 micrometer. So therefore my area becomes 0.49 micrometer, right? So how much it is? Earlier, how much was the area? It is 1 micrometer square. Now how much it is? This one. This area is reduced half.
149. Yes.
So earlier, if there was 1 transistor, then I can put 2 transistors.
Two times.
Because area is less, right? So area is becoming less. So this is called as MOSFET scaling. And because of that, we can put large number of transistors because devices are becoming. Now, if you see this slide, so MOSFET scaling started in 1970. At that time, minimum dimension was 10 micrometer, and it has decreased every 2 years. Then it has become 6 micrometer, 3 micrometer, 1 micrometer, and now it is 22 nanometer. That was in 2015.
So,
Yeah, nanometer means 10 to the power minus 7. Yeah, but right now it is very small. So there is, see, devices are becoming small, right? So we can pack large number of devices, MOSFETs. But what is happening to the performance? You know that, as I have shown, first computer was having just speed of 100 kilohertz.
speed will increase.
Yeah, but as you make devices smaller and smaller, its speed increases. So we will see how its speed increases, right? How its speed increases. And that is the reason right now our processors are having gigahertz speed, 1 gigahertz, 2 gigahertz. So let us understand MOSFET scaling for. So this is the MOSFET, our original MOSFET, right? After scaling, so what we are doing, we are reducing its width and length. In the given area, I can put 2 transistors. Can you see? Before there was only 1.
Yes, yes.
And here 2 transistors.
Okay.
So MOSFET scaling is a process of reducing vertical means vertical dimensions as well as horizontal dimensions by scaling factor S. See, remember there is a scaling factor S whose value is greater than 1. So MOSFET is a process of reducing vertical and horizontal dimensions by scaling factor S whose value is greater than.
Yes.
Now this is the current state 2020, 1970 and 2020. Earlier was 2050. So you can see here, so dimensions has reached to 10 nanometer here. 10 or
Yes,
less than 10.
Hmm.
Yeah, but because of that, there are many problems that here it is mentioned that we will see it as we proceed. Then, once you have understood MOSFET scaling, then I will explain there are two types of MOSFETs. Scaling. One is called as constant field MOSFET scaling, which is also called as full scaling. And there is another type, constant voltage scaling, which is called as partial scaling. Is constant field scaling, there is another name which is called as full scaling. There is another type, constant voltage scaling, that is called as also called as partial scaling. Okay, so let us understand what is constant voltage scaling and what is constant field scaling. Okay, so constant field scaling. So what is meant by field? What is meant by field?
Area.
Field is, I'm writing here, field.
Area.
Field is nothing but electric field.
Electric field.
It is electric field. It is given by V by, where volt by centimeter
By,
are dimensions of electric field. Okay.
yes, sir. Yes, sir. Length and this.
Yeah. So see, when I say constant field, when I say it's a constant field scaling, E divided by R, means if I am reducing V, then I am reducing L also by same scaling factor. Okay. For example, if I reduce V by S, then I will reduce L by S. SS gets cancelled and electric field remains same.
Same. Yes, sir.
So that's why such type of field is called as constant field
Constant field.
scaling.
Yes.
Now see here, these are the parameters of MOSFET. This is MOSFET before scaling. This is MOSFET after scaling. It becomes smaller. These are the quantities, various quantities. Channel length. You know channel length. What is meant by channel length? Yes. Then channel width. Then oxide thickness.
Oxide layer formed.
Then junction depth. Then power supply voltage VDD, threshold voltage VTO, and doping densities, acceptor doping density and donor doping density. So see, after constant field scaling, what happens? Channel length L dash, it reduces by factor S. W, it reduces W dash, it reduces by factor S. Then there is oxide thickness, it reduces by factor S. Junction depth, it also reduces by factor S. Supply voltage VDD, that also reduces by S. So why we are reducing supply voltage? Because this is constant field scaling. We are reducing the dimension, yeah, as well as voltages. All the voltages
will go down.
reduced by some.
Yes.
Then acceptor doping Na, that is increased by S.
That is increased and
doping is also increased by factor. Okay. So this is basically before scaling and after scaling. Okay.
Okay.
These are the parameters of MOSFET. This is for constant field
scaling. Field scaling.
Now we will see what is the impact on performance of MOSFET. Okay.
So
So this constant field scaling. So first we will see what is impact on oxide capacitance. You know that oxide capacitance is CO ox. Okay, so CO ox dash is capacitance after scaling.
After scaling.
Capacitance is given by EO ox, that is oxide permittivity, divided by TO ox dash. Okay, dash means after scaling. And we know that there is a relation between TO ox dash and TO ox. And that relation is nothing but TO ox dash is equal to TO ox by S. So S is in denominator, it goes in numerator. So EO ox divided by TO ox is nothing but capacitance before scaling. So what you can say, CO ox dash or prime and CO ox is before scaling. This is after scaling. After scaling, capacitance increases by factor.
Yes.
Yes. So I can say that in constant field scaling, oxide capacitance increase by factor. Now let us see what is impact on linear drain current. Linear drain current equation is given by this. ID dash linear Kn dash. Kn dash is V1 CO ox W by L.
W by L.
I will just write here for understanding.
C ox W by L.
So here. Okay, here. It's Kn. Kn is basically mu CO ox W by L. Okay, so after scaling Kn dash, what happens? Mu nothing happens. What happens to the CO ox?
Yes, sir.
This becomes S into
S into K, that is C ox.
And what will happen to W and L? W reduces by L.
W with S and L also S. Yes.
Therefore, Kn dash is equal to S times Kn. Yes, because this S gets cancelled. So it is S, means my transconductance increases by S. So that is mentioned here. So Kn dash, can you see here? It is written as a S times K. Then VGS dash. VGS dash is nothing but VGS by S. VT dash is nothing but VT by S. VDS is nothing but VDS by S. VDS dash is nothing but this one. So when you take S square common, यहाँ से S, यहाँ से S, यहाँ से S, and यहाँ से S square. So S square common, this S and this S square gets cancelled, and your drain current after scaling reduces by factor S. So what you can say that oxide capacitance increases by factor S, while drain current increases by decreases by factor
S.
So this is the impact of constant field scaling, right? Now similarly, saturation drain current. In same way, you can prove that saturation current reduces by factor S in constant field scaling. Saturation drain current decreases by factor S. Now let us see impact on power dissipation. Power dissipation is given by current multiplied by voltage, right? Current multiplied by voltage. So current is reducing by factor S. Voltage is also reducing by factor S. Therefore, my power dissipation reduces by S square. ID into VDS is power before scaling, and V dash is nothing but power after scaling.
Power after scaling. Yes.
So my power reduces by factor S.
Factor S square.
Okay.
Yes.
So now we will see delay. Delay, what happens? Tau is delay. Delay is given by CV by I. Now, why this equation is there CV by I? This particular equation is derived from very basic equation. I call that equation is equal to, do you know current flowing through capacitance? is given by C dV
V by
dt. Okay, or if I simplify this, it becomes d or dt, then it becomes C dV by di. So delta t is nothing but tau. C will remain as it is. Delta V is V and delta I is I. Therefore, delay is given by this equation. Okay, so let us call this equation is before scaling. And this is after scaling. So capacitance CAS after scaling, voltage after scaling, current after scaling. Now CAS, you know, CAS is given by total capacitance, that is given by length, area multiplied by, see here, because
COX, yes, sir.
CAS, actually total capacitance is given by WL into COX.
COX.
And
That is
after
with
scaling,
it becomes
it becomes
S.
W by S,
S.
L by
L
S,
by S.
and this becomes S into.
COX and S.
So
COX.
therefore, my capacitance, total
S is
capacitance after
cancelled.
scaling reduces by factor. Yes.
C by X.
Can you see this?
Yes, sir.
Reduces by factor. Yes.
Yes.
And this is voltage
Yes, sir.
scaling. That's why voltage also reduces by factor.
V by S and I is current.
And current also reduces by factor. Yes.
Yes, yes.
So if I substitute all CAS, VAS, and IAS in this equation,
That is scaled
yeah,
decrease like
then I get delay after scaling, that is tau by S.
tau.
So therefore, I
Okay.
can say that delay reduces by factor of S.
Yes.
And frequency increases by, if delay reduces, then frequency increases by.
Frequency will increase. Yes. Okay.
So that's the reason I told you, as we make MOSFET smaller and smaller, its
Yes,
frequency
advantages
increases.
increase.
Yes, its frequency increases.
Yes. Yes.
Now, summary of constant field scaling. This is the summary. Now, oxide capacitance COX, it increases by factor S. Drain current reduces by factor S. Power dissipation reduces by factor S square. Then power density, which is defined as power divided by area. Area also reduces, power also reduces by same factor. And that's why power density remains same.
Okay.
Power, because power reduces by S square.
Yeah, both
And
are
area also
S
reduces by
cancelled.
S square. Okay, so
Right.
therefore power density remains same after scaling.
Yes.
Right. So this is basically constant field scaling. Now there is another type of which is called as constant voltage scaling. As name indicates, in constant field scaling, field is kept constant. And we keep the field constant by scaling voltage as well as dimensions. But in constant voltage scaling, all dimensions of MOSFET are reduced by factor S, while voltages are kept constant. We are not reducing voltages. Voltages are kept constant, right?
Okay.
So
Yes.
therefore, this is quantity before scaling and after scaling. Dimensions W, L, TOX, junction depth,
So they
all
all
are reduced
reduce.
by factor S. But
Oh,
voltages W, VDD, VT, they remain unchanged. They are not changed. They are kept as it is. Okay. But what happens to doping densities Na and Nd? Doping densities are increased by S square. Doping densities are increased by S square. So this is the difference between constant voltage and constant field scaling. So let us see what is its impact. What will happen to the capacitance after scaling? COX prime is capacitance after scaling. So it increases like constant field scaling In constant voltage scaling also, MOSFET capacitance increases by factor. Now let us see what is the impact on linear drain current. So this is the equation after linear drain current. Can you see here? Kn dash VGS dash minus VT dash VGS dash minus VDS square. Now Kn dash, we know that it becomes S into Kn after scaling. VGS, it remains unchanged. It is not changing.
Yes.
VT dash, it's not changing. VDS is not changing. So therefore, if you see this much equation, that is just IDS before scaling. And it is, there is one extra factor, yes. Therefore, in constant voltage scaling, linear drain current increases by factor, yes. While in constant field scaling,
it decreases
by, yes. So this is the difference between constant field scaling.
This oxide capacitor linear, it increases in the scaling. Voltage scaling, and in that it decreases. Yes.
Saturation current. So saturation current also same thing happens. This Kn dash
that
increases while voltages are same. So therefore,
saturation will
increases by factor, yes. And what happens to the power dissipation, because voltage remains same, but drain current increases, so power increases by factor.
Yes.
Now impact on delay. So it is same way we calculate the impact. Here what happens, your voltage remains constant. While current increases SI, current increases by factor yes. So when you substitute all, because capacitance reduces by factor yes in constant voltage as well as constant field, but voltage remains same, current increases by factor yes. When we substitute all these values, your tau delay reduces by s square. Here delay reduces by yes,
S only.
here reduces by s square, right? So delay reduces by factor s square, while hence frequency increases by factor s square. So suppose I want more frequency, then which scaling you will prefer?
Voltage
scaling you will prefer, right? Now let us see what is the summary of MOSFET scaling. So oxide capacitance, summary of constant voltage scaling. Oxide capacitance increases by factor s, right? Drain current ID increases by factor s. Power dissipation increases by factor s, and power density increases by s cube. In constant field scaling, power density remains same, but here it increases by s cube. So I will tell you how it is, how it increases. Okay, now just see power before scaling is given by I into, right? Area before scaling is W into L. Power after scaling becomes S times
IV, I and
S times current
times
voltage.
P.
Yes. And area
into
reduces by S square.
Yes.
Okay, ये भी S से होता है. So when you take the ratio, so ये S cube से increase होता है. So in this way, after scaling, power increases by S square. So basically, this was the what is lecture objectives. What you have learned?
Scaling.
You have learned scaling.
Scaling is better.
We have seen the history of MOSFET, history of electronics, how our processors are evolved from, computers are evolved from first generation computer to today's smartphone, where very high computing processors are there. And all this has happened because of the MOSFET scaling. MOSFET scaling is process of reducing the dimensions, vertical as well as lateral dimensions of MOSFET by some scaling factor, whose value is greater than 1. There are two types of MOSFET scaling. One is called as constant field scaling and other is called as constant voltage scaling. In constant field scaling, MOSFET dimensions as well as all voltages are scaled by same scaling factor, and therefore field in MOSFET remains same before scaling and after scaling. Right?
Oh, yes.
Yeah. Delay also increases, delay reduces by factor S, while power density same. In constant voltage scaling, voltages are kept constant while all dimensions are reduced by factor yes, that is scaling factor. And in constant fields, constant voltage scaling, delay reduces by factor s square, while power density increases by s cube. Yeah. When there is no power constraint, but if you want high performance, then constant voltage scaling is used. But when there is a power constraint, then constant field scaling is
scaling. Yes.
So let me know, do you have any difficulty?
No, sir.
You understood everything?
Yeah, yes.
Yeah, so I will put the slides on this one, our Moodle course. Okay.
Yes. Okay.
So any question?
No, sir. No, sir.
Okay, then we'll stop here.
Okay, sir. Okay, sir. Thank you, sir.